Okay, check the sound. My microphone, perfect. Now we're gonna start with the longest one. I like titration curves. I like the titration problems, but they're long. Okay, so we're gonna go for 17, and I'm gonna explain a little bit. Okay, here we have a strong acid plus a strong base. Is the titration of 40 milliliters of hydrochloric acid with NaOH. They don't tell me how much because we're going to be adding NaOH. So it's two, an acid, a base, and both of them are strong. So we got NaOH gives me the salt plus the water, NaCl plus the water. Now let me make sure of something here. Okay, you need to write down the equation because we're going to be working with the moles and stoichiometry. So I want you to consider that and don't forget to write it down. So let's look at a PowerPoint of the titration curves. And basically what we have here is first of all, an acid-base indicator. That I'm going to explain it in class. But this is what we need. In a strong acid and a strong base titration, you got and you start, right? You're adding the base the base. So we got a low pH, the pH of the acid by itself. In this case, is hydrochloric acid with NaOH and a zero point 0.1 of both. With 0 milliliters of NaOH, we got a pH of 1.0. You got this on the PowerPoints, but what you need to do is verify because the volumes are not exactly the same. They change on the exercise, on the question. Okay, 30. We got 30 here, and the pH is 185. But the second one would be, 39.30, I think. The second one, which is not here. You see? It's not here. So you're going to have to do it, but it's not a big deal because these are the equation. While you are before the equivalent point. At 0, right, you have nothing. You have only the acid, and the pH depends on the acid, on the dissociation of the strong acid. Okay, 100% ionization. And then the base, which is this one, okay, is the minus log of the concentration of hydronium, and the concentration of hydronium would be equal to the concentration of the acid because it's a strong acid. Then it comes a little bit more complicated because then we have to do the stoichiometry. What I explained it to you, what I explained, because as we are adding aqua solution, we have a new volume, so the molarity is going to change. The molarity of the acid and base is going to be less. Okay, you're going to see, but the number of moles are the same. So it changes the pH before the equivalence point. Now, after on the equivalence point, the pH is 7, a strong acid and a strong base. But after, you have an excess hydronium. So let's do step by step each one, and then we'll do other curves like the weak acid with a strong base. Okay, so we got here a strong acid and a strong base, and the letter A is asking for the pH at what? At 30.00 milliliters. The first thing you have to do is calculate the moles or millimoles. Some professors, some teachers use the millimoles. I don't mind using the moles, but the milliliters you have to convert it to liter. So initially we had all of this is always in the flask, and it's 0.040, and we put all the sig figs liters of acid with a molarity of 0.1000. To find out the moles of acid, moles of HCl, is going to be, we're doing the HCl initially. We don't have to do the pH calculation, but we need to know how many moles you have present in the flask. And it's going to be 0.004 40 moles. And we got here 0.00440. Okay, now let's go ahead and calculate the number of moles of NaOH that we added, and I'll tell you why. Because remember, the NaOH that we add is going to react with the HCl present and to form NaCl. So if you got 30 milliliters of NaOH, that is going to be 0.03 liters. So that is going to be 0.3 liters. 1, 2, 3. And that is going to be that the moles of NaOH added is going to be 0.003 moles, because we multiply the liters by the molarity, and the molarity is 0.12, like the acid here. Okay, so the number of moles added on letter A is 0.03000 liters multiplied by 0.1000 liters molar is going to be 0.1000 molar. So the moles of NaOH added is going to give you 0.003. So let's go with the reaction and the stoichiometry. So here we added 0.003. So initially we have this, okay? What would change? Okay, here you got 0 and 0. What would change is all the NaOH reacted with the HCl. So you're going to have the limiting reactant is the NaOH. I don't know if you understand it like that, because the handwriting and everything is horrible. So nothing NaOH, because all the NaOH reacted 30 milliliters with the acid, but you have left 0.010 of acid. Okay, and here you have of NaCl plus 0.00300. You do the same as the ice table, but it's called ICF, and it's 0.00300. Why? Because once all the NaOH, it doesn't react anymore. So what you're going to form is the same amount, a 1-to-1 number of moles of NaCl than the NaOH. That's stoichiometry. So we got here, make sure. I'm not going to do it again. I'm going to put pause, and I'm going to try to redo it in a... Okay, let me continue. So I put it a little bit nicer so it looks better, so you can visually see it. We got initially, okay, 40 milliliters of the acid. So we got 0.0040. And we added 30 on letter A of 0.100 molar. So it's a 1-to-1 ratio. So if we compare the moles of each one, okay, the NaOH is the limiting reactant, because we added less than what we had of acid. But you're going to have, if you subtract this, right, the change would be all the NaOH reacted with the HCl, you have an excess of HCl, and you have the NaCl form, which is the same as the NaOH. But for the titration, I don't care about the NaCl for now. what on the quantity. What I care is that you have left acid here. Okay, so the acid, the moles of acid in excess or left, right, without reacting, are gonna be 0. From the 0.004 minus 0.003, 0.100 moles of HCl. This is HCl. So, but now to find the molarity of the HCl, so we can find the pH, sorry, is the 0.001000 moles. But be careful here because now the concentration is different because you add 30 milliliters of solution. So if you had initially 40 from the acid and 30 from the base, your total volume now is going to be 70 milliliters, which is going to be 0.070 liters. So the molarity of the acid would be the moles of acid that you have left that didn't react divided by the total volume, which is, I'm going to write it down again, breaking down 0.30 liters plus, initially we had 0.40 liters. So this is equal to, I'm going to put it on the bottom, HCl. I'm breaking it down. That's what I'm doing. 0.001123 milliliters divided by, I'm sorry, moles. Oosh. I think it's faster just to do this. Sorry. Scratch this. And this is going to be moles. Okay, 0.00100 moles from the excess acid. Okay, this is total volume. The total volume. Okay, and this is going to be, okay, divided by 0.070 liters. The molarity of the HCl would be equal to the concentration, of course, and it would be equal to 0.01429, which this is a concentration of H3O. It's a strong acid, ionized at 100%, so it's equal. So the pH would be equal to minus the log of, well, 0.01429. I'm already giving the concentration. And the pH would be, on letter A, 1.85. Okay, we have a very strong acid, very little we have left acid, so the pH makes sense that it's acidic. Now we got 39.30 milliliters of NaOH. So again, we have the same amount of moles of acid initially, because we're going to do it all over again. Okay, 0. You can do the difference, but I do not recommend you to do it. 0.0 between 39.30 and 30. You add 9 more. But no, I'm going to do it the other way. Takes a little bit, but you got 0.0040 moles of HCl. And you got here added 39 milliliters. It's going to be that I use this. Okay, it's gonna be, this is 0, and this is gonna be 0.03930, okay, liters of NaOH. Now you multiply by molarity by 0.1 moles per liter equals to 0.003930. So let's do the equation and the number of moles we want to see. You already know that we still have HCl in excess. Because basically, if the concentration of a strong acid on a strong base is the same, it's a 1-to-1 ratio, and in this, it's if it's a 1-to-1 ratio also, you have to have the same number of moles on both for the equivalence point to have a pH in which both of them reacted 100%. So you have to have the same volume. Okay, so initially, let's put it at 0 before you start it. Okay, and here you got 0.0040. Here you added 0.003930. I don't know if you understand what I'm talking about adding the volume. Instead of putting this from the beginning, from the starting point, you can start adding, but I do not recommend you to do that. It's going to be a mess. In fact, I don't think the book does that. Okay, so here 0 and 0 water. Let's ignore the water because the concentration doesn't affect the pH. Okay, so we got minus 0.003930. This is 0.003930. Why? Because this is steel, and then you're going to form here, that's the change, plus the same amount, 0.003930. How do I know? Because this number is smaller than this. That means that this is still the limiting reactant, and this you're going to have an excess. So the final, on the letter B, the final moles of acid is going to be 7.5, 0. By 10 to the negative 5. Here you have 0, and here you have 0, which we don't care, but I want to finish the whole table, meaning that it's not going to affect. The only thing that affects is now the volume. So I can do it faster. The molarity of the acid of HCl would be the number of moles. It's horrible, this. Well, let's say it like that. The molarity of the HCl would be the number of moles left. We still have an excess of hydrochloric acid. 10 to the minus 5. The pH should give us higher. And divided by the total volume. Be careful, you have to add the total volume, which is in liters, 0.04 liters plus 0.03930 liters. So the molarity would be of the HCl would be, let's add the one on the bottom, 7.0 or 7 by 10 to the negative 5 divided by 0.0793 liters. Okay, this is smaller moles. So the molarity is going to give you of HCl is going to give you 8.83 times 10 to the negative 4 m, which is the concentration of hydronium. And that would be, from there we calculate the pH, 8.83 by 10 to the negative 4 m. So I'm guessing you already know how to calculate the pH, which is the minus log of this concentration. So this gives you pH of 3.05. If you see, our pH is increasing with the addition of NaOH. And finally, no. How many parts? We have like 4? No, this is the third one. Finally, we are adding, okay? How I said, if you've been asked for the addition of 40.00 milliliters of NaOH is a 1-to-1 strong acid strong base, so the pH would be 7. Okay, that's the equivalence point. So here we do the same thing. You have initially 0.0040 moles of HCl. And I don't have to write the equation. 52.0 milliliters of NaOH, 0.1 molar. That gives me 0.0050 moles. So now you have of NaOH. Now you have an excess of NaOH, which is going to be all the acid reacted to convert it into salt. I have to do that. Even though I said I'm not going to do it, I like to do it so and break it down. NaCl plus water. So here you got initially 0.00, you haven't had anything, plus 0.00520, because we're using from the beginning. Okay, like we started that and we added this. So initially at the beginning we had nothing here. So now after adding 0.0520, what is going to be the change? Okay, this is the one that is greater. So the limiting reactant this time was going to be the acid, okay, because you have more volume. This is going to be 0.0040 plus, and this would be minus 0.00400. So that gives you, the final gives you, this is gone, all the acid. Now we have an excess, and it's going to be 0.2100. And there's no sign, moles. And here you got 0.004. How do you know it? Well, with the number of moles you converted. You know you have a 1-to-1 ratio. So you know already that it's the HCl is all gone. And in fact, you put the both of them and you automatically know which one is in greater amount, which is the NaOH. That's why I said I'm not going to do it, but you have to do it, the equation. The ICF. So you got here, okay, that the concentration, but now this time would be a OH. Why? Because H3O is all gone. So you're going to have to find the OH and then subtract it and find the pH. POH and then subtract it from the 14. So we got here that we have 0.00, that's the excess of sodium hydroxide, moles, and you're going to divide it by the total volume. So what it would be the total volume here? You add 52.00 milliliter, which is 0.0520 liters, plus what you had initially of the acid, liters. So this is going to give you that the concentration of OH equals 0.00120 moles. You divide it by, this gives you 0.1020 liters. So the concentration of OH negative would be 0.01176 molar. So the POH would be equal to 1.93, and the pH would be 14 minus 1.93. So now you're getting into a basic solution, 12.07. And as NaOH is a strong base, you get up a lot to a high pH. Okay, I'm not going to have time to record another one because it's another exercise and we have to go step by step, and it's different. It's a weak acid with a weak base. The ones that are the same, I think they're the number 19 would be the same also, a weak acid with a strong base, sorry. So I don't have to do the 19. By the way, on the PowerPoints I posted, you're going to have the formula. Then what I have to do, what I'm going to have to do is the diprotic or triprotic acid. That's a different story. It is. So finally, then the last problems is applied to KSP. And I'm going to do a few. Tonight, I'm going to do one or two. We have the classes tomorrow, but tomorrow night, I'm going to, early evening, like about 6 o'clock, I'll do more. So tonight, I'm probably going to record, this is the third one, I'm probably going to record 2 more, at least, so you have 5, and then record the last one tomorrow, Tuesday afternoon. Not sure, I'm going to try. Okay, so, but I need to go now, and I would have to start a new whole video, and now, because it's too much.